Hello everybody, this is Mr. Dowse, and today this is going to be the recording for the first of two lessons on exponential growth and exponential decay functions. We're going to see, I'm going to start with an equation here, y equals a times b to the power of x. And if you've been in my class the last few weeks, we've gone over this equation several times with different kind of rules, like the quotient rule and the power to power rule and things like that. But I'm going to relabel all these variables here. X is going to be exponent. And then we have B, I'm going to call this the base. And then A is going to be the coefficient. Now A and B can be any numbers. They can be like, are going to be numbers, I guess I should say. Like A could be a 1, a 2, a 3. It could be a -1, -2, -3, something along those lines. And then B, the base here, is going to be any number greater than 1, and I'll go over more of that here in a moment. But this is what I started off the first lesson on in my class a few weeks ago, was labeling these variables in this equation. Now, for exponential growth and exponential decay functions, I'm actually going to call this base a couple other names. I'm going to call it the rate. Or I could call this the growth factor, or decay factor, something along those lines, or factor of decay, factor of growth, something along those lines. Today we're going to be dealing with some word problems, or in at least the next lesson, the second part of this. So if you ever see the word rate or a growth factor or decay factor, that's a dead giveaway that that's going to be this variable b in this equation. Now this coefficient I'm going to label as the y-intercept. We're going to be graphing this equation, and so the y-intercept is where the function crosses the y-axis, and when we get to that point you'll see what I mean. But just to indicate, there's a couple differences here over what we did last few lessons, where we're now going to start graphing and dealing with some word problems with the growth of decay and growth and decay exponential functions. So if I jump onto this over here on the left, it says in an equation, an exponential growth or exponential decay function is a nonlinear function of the form y equals a times b to the power of x. Now that's very important here. Exponential functions are always going to be raised to the power of x. For example, if I had y equals 3 times 2 to the power of x, this is going to be an exponential function because this x is the exponent. So that's very important. Versus if I had y equals 3 times x, since the x is not the exponent, this is not an exponential function. So we'll be going through a couple example problems more like this, where is this an exponential function or not? And we'll explain why or why not these are exponential functions. So again, the x is the exponent on exponential functions. If it's not the exponent, then it's not going to be an exponential function. So this is not exponential. This is an exponential function. And then there's a couple of key factors here. A cannot be a power of 0 or equal to 0. If I plug 0 into a in this equation, 0 times anything is just going to be 0. So nothing's going to happen. So we can't have a value of 0 here. A can be any positive number or negative number, but it just can't be 0. B cannot be equal to 1. If I plug 1 in here and I raise 1 to a power of anything, it's just going to stay 1. And when you graph it, it's just going to be a line that goes across the graph, and that can't happen. And also B has to be a value greater than 0. So B cannot be 0, and it can't be a negative value, and that's going to be important here in a little while. So I have a linear function going on the left, and I have an exponential function happening on the right. The linear function, if you know the form of y equals mx plus b, where m is the slope, and then this b is the y-intercept. And then exponential function, again, we have the form y equals a times b to the power of x. So a linear function follows this form, an exponential function follows this form, and if you look, when I'm incrementing from 0 to 1, we're increasing by 1 on the left side of this table, and when I look at the right here, I'm adding 2 to get from 2 to 4, 4 to 6, 6 to 8, and so this adding of 2 is the m. So whenever you're adding on a table, or you're adding values at a constant rate on the y, this is a dead giveaway that this is a linear function. If I were to plot this, it'd be a line, a straight line. Versus exponentially, notice on the left here, these are incrementing by 1 for the x values, but on the right side, it's not adding by 2. It looks like it is at first, but in reality it's doubling. So I'm going to say times 2. So if I take 2 times 2, it gets me 4. 4 times 2 gets me 8. 8 times 2 gets me 16. And since we're multiplying here, this is a dead giveaway that this is going to be an exponential function. Exponential functions, we multiply by a factor from the previous value of y to get the next value of y. Versus on a linear function, we're incrementing by adding or subtracting. Exponentially, we're going to be multiplying. So that's a dead giveaway. So this here would be my base or my rate. So just something to kind of keep in mind. So if I look at these examples further down, determine whether the table represents a linear or exponential function. If I start at the first one here, again, these are all incrementing by 1 on the left, which is what we need to happen here for this to be kind of easy to tell if this is exponential or linear. And if I look at the right here, it looks like I'm subtracting by 4. But then if I go to 4 to 2, it looks like I'm actually subtracting by 2. So since this isn't increasing or decreasing at a constant rate, this is not a linear function. This will be exponential. And in reality here, this is dividing by 2. It looks like it at least. But whenever we're dealing with exponential functions, if you look at the equation, a times b, it's not a divided by b. So I need to come up with an equivalent b where it's dividing by 2. So if you take 2 and you divide by 2, it's the same thing as multiplying by 1/2. If I take 8 times 1/2, it'll get me 4. 4 times 1/2 will get me 2. 2 times 1/2 will get me 1. And so in reality here, my b is going to be equal to 1/2. We're multiplying 8 by 1/2. We're not dividing by 2. Your exponential functions can't divide by 2, but the equivalent of dividing by 2 is multiplying by 2. So that's just something to keep in mind. Looking at number 2, the values on the left side are all incrementing by 1. And the values on the right we're actually adding by 4. So since we're adding a value to get from one value of y to the next, this is going to be a linear function. And again, because we have a slope here, a constant rate of change is going to be 4 in this case. Looking at number 3, again, the left side is incrementing by 1. The right side is actually subtracting by 3. And since this is changing at a constant rate by adding or subtracting, this is again slope, so this is again a linear function. And if I look at the fourth one, everything's incrementing by 1 on the left. And if I look at the right here, it's not so obvious to tell. It definitely isn't adding or subtracting because they're not changing at a constant rate. But if I start at the bottom one here, from 2 to 8, I need to multiply 2 by something to get to 8. Well, that's by 4. And if I go backwards, 1/2 times 4 gets me 2. And then also 0.125 times 4 gets me 0.5. So this is going to be my constant rate of change. And this is going to be an exponential function. So looking at 5, 6, and 7, determine whether the equation represents an exponential function and explain. I'm going to go right back to the top here and indicate that, again, an exponential function is in the form of y equals a times b raised to the power of x. A cannot be 0, b cannot be 1, and b has to be a value greater than 0. If all of these characteristics are there, then we can say that it's an exponential function. So if I look here, y equals a times b to the power of x. I have my exponent here. That's good. My 6 looks like it's a negative 6, so that b looks like it's a negative value, which it can't be. Now keep in mind here, there aren't parentheses around the 6, so that negative sign is not actually grouped in with that 6. I've mentioned that in a previous video, that if you have parentheses around a negative value and a 6, that it groups those values together. So like negative 6 in parentheses, this would be a negative 6. Negative 6 here is actually a negative 1 times 6. So in reality, my b is a 6 in this case, and my a is a negative 1. And so I know it's a little tricky here, but again, since there aren't parentheses, this negative is not grouped with a 6, so this is actually a negative 1 times 6. So my a is my negative 1, my b is a 6, and I have an exponent that is an x, and that follows all these different properties of an exponential function. So this is actually an exponential function. So I'm going to just put exponential, and the reasoning is, again, we have an x for our exponent, our b is 6, our a is -1, it follows all those properties, so this is an exponential function. If I look at the second example, again, y equals a times b to the power of x, so y equals a times b to the power of x. I have my x as an exponent, I have my a is a 5, but my b is equal to a 1, and I can't have a value of b equal to 1. So this is not an exponential function, so it's not exponential. And again, the reasoning is b cannot be equal to 1. And I'm going to grab a calculator super fast here. I just want to explain the reasoning behind why that is. Let me show you the fifth example here on the calculator, and then I'll show you the sixth example, and you'll see there's a dramatic difference in the function here. So if I plug in an exponential function, it's going to look, so -6 raised to the power of x. And if I graph this, an exponential function, this is an exponential function here. So exponential functions have a characteristic where one side is kind of flat, and then the other side either ramps up quickly or ramps down quickly. In this case, it's ramping down quickly. So this is like an example of an exponential function. Versus if I plug in this next one, 5 times 1 to the power of x, and I graph this, notice it's just a straight line. So on the table here, my y value is all 5s on the second equation, and that's because whenever we have a rate of 1, we're multiplying 1 to the power of 1, 1 to the power of 2, 1 to the power of 3. No matter what, this b value to the power of any value is going to be 1, so it's going to be 5 times 1, which just gives me a line. So that's the reasoning why b can't be equal to 1. It just gives us a line. Then if I look at this next one here, so y equals a times b to the power of x. Notice this is not exponential, and the reasoning is because the x is not the exponent. This x is 7 times x to the third power. I have a 3 as my exponent, not an x. So x is not the exponent would be my answer on why it's not an exponential function. Is not the exponent. So there we go. So moving on here, evaluate the function for the given value of x. So what this really means is I have an equation here, y equals 3 to the power of x, but they want us to put 5 in for x instead of x as in for x. So if I were to plug this in the calculator, so I'm just going to go and do 3 to the power of 5, that gets me 243. So 243. So if I plug in 5 in for x, that gives me a value of 243. So that's all we had to do there. If I look at the next one, y equals 1/4 to the power of 3. I can plug this in my calculator. Again, we're plugging in 3 for x, so I can do 1 divided by 4 raised to the power of 3, and I get a decimal of 0.015625. So 0.015625. In my calculator, I can just hit math, enter, and it will also convert it to a fraction, to 1/64. But since we've gone over these kind of rules here recently, I'm just going to actually solve this using the power-to-power rule. So 1/4 raised to the power of 3 is the same thing as 1 to the third power over 4 to the third power. And this is just 1 times 1 times 1, which is 1. And this is 4 times 4, which is 16, times 4 again, which gets me 64. And so that's an alternative approach of finding this problem as well. I would accept either the decimal or fraction, but just a good time to do extra practice. Then if I look at number 10, y is equal to 3 times 4 to the power of 4. So we're plugging in 4 for x. And so this is 3 times 4 raised to the power of 4. Notice whenever I type things in the calculator, I'm typing in it exactly as I see it in the problem. That'll just make sure you don't make any simple mistakes. And in this case, I get 768. So 768 is the equivalent to 3 times 4 raised to the 4th power. Just going to move on here a little bit more. If I jump into exponential growth and exponential decay, this is the main important part of the lesson that we really need to know. Actually, I'm going to stop this right now just so I don't make this video too long. So I'm actually going to add an additional part to this video. So I'm going to stop this right now. And just as this is the intro to exponential function notes, and then I'll add a second part here to kind of go over more details on exponential functions. That's it. Have a good day. Bye.